find product constant. As you can see here, we only have our reactants as water because we're looking for the auto-ionization of water. What is being released? Our H3O plus, which would be an acidic solution. We're also releasing OH minus, which would be a basic solution. We're going to be putting all of them into our equilibrium constant expression. As we can see in our denominator here, we have two H2O molecules. Obviously, these are liquids, so they can't be expressed into our expression. So we're just going to multiply it on the right side. If you do it on the right side, we have to do it on the left side. So as you can see over here, it is integrated within the KEQ. This is going to be squared. So technically, the concentration here is moles per liter. You got to do that twice. You have moles squared over liter squared as shown here. This is moles per liter. This is moles per liter. So technically, these are moles squared over liter squared as well. So if you square root this side, you can also square root that side. So what do you end up getting? We just end up getting within here one molecule of H2O ionizing and producing, for our equal sign here, one molecule of H3O and one molecule of hydroxide. So technically, our Kw is only our product over here, our hydronium and our hydroxide. Note, Kw is actually 1 times 10 to the negative 14 moles per liter. What does this value signify? It signifies that this here is the concentration for the auto-ionization of water. How do we know that? Well, look over here. Kw, what is integrated within this Kw? As you can see up here, what is integrated? Our KEQ and our H2O. So H2O is integrated within our KEQ. So technically this is equal to our products. Okay, so this auto-ionization of water, okay, is 1 times 10 to the negative 14 because 1 times 10 to the negative 14 is our product. Okay, so they are all equal to each other. Lastly, our hydronium and our hydroxide are inversely proportional because they are beside each other. And if they equal 1 times 10 to the negative 14, as we indicated down over here, well, what is this value and what is this value? If this increases, technically this should decrease, right? If this increases, this should decrease. So how do we get the values for each of these? Well, we could just square root 1 times 10 to the negative 14. So if you do that, you get 1 times 10 to the negative 7 and 1 times 10 to the negative 7. That would be both respectively. Well, if H3O plus is greater than hydroxide, this would be an acid solution. If it was the opposite, this would be a base solution. And if they're equal, this would be a neutral solution. Based on the Chatelier's principle, if additional acid is added, of course, our hydronium concentration is obviously going to increase. Similarly, if additional base is added, of course, our OH minus is going to shift and there's going to be more of it being increased and produced as well. Let's have a look at this question over here that has this concentration of hydroxide. As you can see, it's much greater than 1 times 10 to the negative 7, which means whatever value that we get, okay, for hydronium concentration, it should be a lot less because this here is a lot more than our baseline of 1 times 10 to the negative 7. We're just going to be putting that over here. You can't divide this by 0.0025. You do the same thing over on this side. So what you end up getting for hydronium, 4 times 10 to the negative 12, which is much smaller than 1 times 10 to the negative 7. That makes sense. Please try this question on your own. This is the green question of the day, and I'll be giving you the answers shortly. This is the answer.